This formula we got. Mu 0 I r square multiplied by r to the power 3 by 2. This is the, if there are n number of turns in the coil, then we will use this formula. They are getting my voice clearly.
Yes, sir.
I'm checking my net speed. Just a minute. No, it's fine. So this formula, remember, when there are n number of turns in the coil, then you will simply multiply capital N with the magnetic field, this formula. Okay, so you will get finally this formula. So I am taking one question on this. So this is the question. Suppose here are two coils. One coil is this and another coil is this. This coil in YZ peg. This coil is in YZ peg. And this coil is in XZ plane. In XZ plane. Okay. Now we have to find the magnetic field at this point P. We have to find the magnetic field at this point P. Okay. So see, this is the coil, and this is P point is on the axis of the coil at a distance of X. Okay. And this is another coil, coil number 2, and this point P also lies on the axis of this coil, and this point is also at a distance of small x. So what we will do, we will just calculate the magnitude first of magnetic field uh, due to this coil and this coil, and we will convert that magnitude into the vector form by using the modified right hand rule. Okay, so this formula we will use. Magnetic field at any point on the axis of the current carrying coil is given by mu 0 IR square 2 times of R square plus X square to the power 3 by 2. So magnetic field at point P is equal to the magnetic field due to the coil 1 at point P plus the magnetic field at point P due to the coil number 2. So for the coil number 1, we will use this formula, and for the coil number 2, we will use the same formula. Okay.
Yes. Okay.
So this we will use mu 0 I is the current, means both coil have the same current. Irrespective of the direction, magnitude of the current is same. Mu naught I, R is the radius of both the coil, R square 2 times of R square plus X square to the power 3 by 2. And now this is for coil number 1. So when you will apply this, coil is in YZ plane. So the direction of magnetic field will be along the x-axis. Will be along axis. Negative or positive, we will decide by modified right hand rule. So just
Okay,
apply
sir.
the modified right hand rule. So this direction you will get, and this direction is the positive x direction. So you will multiply this with I cap. Now the magnetic field due to the second coil is also same, mu 0 I r square divided by 2 times of r square plus x square to the power 3 by 2. Now here this second coil, see the second coil is in xz plane. So direction of magnetic field will be along the y-axis. Okay, along the y, negative or positive, we will decide it by the right hand rule. Just uh, hold the current carrying coil. Imagine that you are holding the current carrying coil along the sense of current. Okay, and your thumb will give you the direction of the magnetic field at the center point. So at the center point, you will get the magnetic field in the downward direction, means negative y direction. So here you will multiply with minus j cap. Okay, just
Okay.
apply the right hand rule here in this. Okay, so this is your answer. You can take this term common, and you can write your answer in the vector form. Magnetic field at point P is equal to mu 0 I r square. This is 2 times of r square plus x square to the power 3 by 2, and this is I cap minus j cap. This is your magnetic field at point P. Okay.
Okay.
So due to this coil in YZ plane, V1 is along the x-axis. V1 is along the x-axis. This is the direction
Yes,
of
sir.
V1. And for V2, the direction is this, negative y-axis.
Yes.
Just copy this. Take the screenshot.
Yes. Done, sir.
Done.
Done, sir.
So for solving the numerical and the physics, for the physics there is a requirement of these. First, you should know the basics of differentiation, the basics of integration. You have seen that we are doing integration again and again
Yes,
when
sir.
we are driving any formula. So not very deep knowledge of integration you should have, but the basic thing you should know about the integration. And you have also seen that there is a use of vectors also.
Yes, sir.
Vectors is very important part, but you should know the basics of the vector. And another thing you should know the calculation, how to calculate something. Suppose I am giving any calculation, any expression, how to make that expression in the easy way. And another thing is the geometrical knowledge you should have, geometrical concepts you should have. Okay, means what is the triangle, what is circle, what is the area of circle, and all that. Okay, so now this coil topic is finished. Now we will discuss the Ampere's law, Ampere circuital law. So Ampere's circuital law. Ampere is the name of the scientist. Circuital law. Circuital means something which is you can say closed. Okay, and law means law. Just a minute. Hmm. So Ampere's law. Just a minute. Now see, Ampere's law is this. This is the statement of Ampere's law. First, read the statement. Line integral of magnetic field along along a closed path. Closed path is mu zero or mu naught times the total current passing through the wire enclosed by the loop. Okay. So this I am explaining with the help of example. You have this current carrying wire carrying a current I, and this is the straight wire. So what I am doing, I am considering a loop, circular loop around it. I am considering a circular loop around it.
Okay, sir.
Then what I will do, I will do the line integral of magnetic field. Like the integration we have, no? We will do
Yes,
the integration along the length of the circle, along this the length of the circle, or this is also the closed loop, and this closed loop is also known as the Amperian loop. Amperian loop. So this is a current carrying wire and this is the Amperian loop. And for the straight wire, you will always choose, for the straight cylindrical wire, you will always choose the circular loop. Okay, I will write the
okay,
point also, means uh, how you will choose the loop. Okay, so this
okay,
is the mathematical statement, means B dot dl is known as the line integral of magnetic field, is equal to mu zero times of the current carrying this wire, eh? Current carrying this wire and this wire, this loop enclosing this wire. Okay, so you
okay,
will multiply this I here. Okay, take the screenshot of this, but you should remember this thing, line integral of magnetic field. This thing will be used again and again. This thing will be
okay,
used
sir.
again and again now. And the loop for the straight wire, you will always choose the circular loop.
Okay, sir. Done, sir.
So the thing is that here line integral of magnetic field like B dot dl is equal to mu naught times of the current enclosing by the loop. Current enclosing by the loop is I is the current enclosing by the loop. So see this. This is a loop. Here is a loop. Loop means you can means closed loop. Okay.
Okay, sir.
Now suppose I am doing this. So this will not be considered as a closed loop because this is open from here.
Yes, sir.
So here is a closed loop. This is a closed loop, and this is the direction of the loop. Okay, this is the direction of the loop. You
Yes.
can take the direction of the loop. Okay, now how we will decide the direction of the loop? For that, yes, I am telling what you will do. You will just point your thumb in the direction of the current.
Okay,
Point
sir.
your thumb in the direction of the current, and the curvature of your finger, the sense of curvature of your finger will give you the direction of the loop. So here you can see the current is in the upward direction. When you will curl your finger, this will
Yes, sir.
be anti-clockwise. So this
Yes,
will
sir.
be the direction of the loop. Okay.
Okay, sir.
Yeah. This is very simple thing. And now here, this direction is already given, and
Yes.
one current is given, another current is given, another four currents are given.
Yes, sir.
We have to calculate the line integral of magnetic field. First, we should know what is the line integral of magnetic field. Line integral of magnetic field is this: magnetic field into dl. This we want to calculate, and according to Ampere's law, this is equal to mu zero and the total current enclosed by the loop. Total current enclosed by the loop.
Okay, sir.
So this is the total current enclosed by the loop. This is equal to mu zero. And now you will take the outward direction as positive. Okay, you can take the direction according to you also. You can take the downward, inward direction also positive. Okay.
Okay, sir.
Yeah. So I am taking the outward current as positive. So this current is outwards or inwards? This current. This is the current.
Yes, sir.
This represents the inward current, because here you can see this cross represents the inward direction and this dot represents the outward direction. So here is some current which is going inside means inwards
Yes,
along
sir.
the negative z axis. So this and this current will be positive. I2 and I3 current will be positive. So you will write I2 plus I3, and this I1 will be negative because this is going along the negative z axis.
Okay,
So
sir.
I have considered the negative z axis as negative, minus of I1. So this is your answer, and this current you will not take because this current will not be enclosed by the loop. So this is the benefit of the
Okay, sir.
Ampere's law. We have calculated the line integral of magnetic field, because we know that line integral of magnetic field is equal to mu naught into I. Okay, according to the Ampere's law, Ampere's circuital law.
Okay, sir.
Let's copy this.
Done, sir.
So now the question is how we will decide the loop will be circular, the loop will be square. So for that, you should keep some points in your mind. Means that why you are considering the loop, because closed loop, because we want to
Yes, sir.
simplify this. We want to simplify this term, line integral of magnetic field. So there is a criteria to choose the Amperian loop. I have written some points here. Criteria to choose Amperian loop. So why we choose, how we choose the Amperian loop? Okay. So we use Amperian loop to simplify the line integral of magnetic field. Okay. Line integral of magnetic field, that is V dot dl, and the loop should be closed loop. Okay, it should not be
Okay, sir.
open, and magnetic field should be uniform throughout the loop, and the magnetic field line should be tangential, or you can say the perpendicular to the loop. For the straight and the cylindrical wire, uh, this point is very important. Uh, for straight and the cylindrical conductor or wire, Amperian loop is circular. Amperian
Okay,
loop is circular. So these are the five points you should keep in your mind while choosing the loop. So for the, you should
okay, sir.
remember that for the straight wire you will choose the circular closed loop. Okay, just copy this.
Okay, sir. Done, sir.
Now I will solve one question by using this Ampere's law. Then here we will calculate the line integral of magnetic field. Then the whole story you can understand. So this is the question. Proof Ampere's law, Ampere's circuital law, and I'm just taking this wire. Okay, so so we have to prove that V dot dl means line integral of magnetic field is equal to mu 0 into I. Proof Ampere's circuital law. This is Ampere's circuital law. We will prove. So for proving this, we will take a long wire. We'll take a long wire, and this is a long straight wire. So I have told you for the straight wire, while you will consider the loop around the wire, you will choose the circular loop. You will choose the suppose I have choose as the circular loop. of suppose radius r, of radius small r. We know that now see the loop, and we know that and this current carrying wire is passing through the center of the loop, and due to this current there will be the, suppose I am taking one point here,
Yes.
I am taking one point here, and due to this current carrying wire there will be the magnetic field at this point, there will be some
Yes.
magnetic field at this, because the current carrying wire will generate the magnetic field we have discussed earlier, Biot-Savart law. So when you will find the direction of the magnetic field at this point by right hand rule, okay, you will get direction of magnetic field will be tangential to this. You will get the direction of the magnetic field which will be tangential. Okay, no problem. Now it's fine. Now I am taking another point on this circular loop. Suppose here I want to find the direction of the magnetic field and the magnitude. So because this distance is r, this distance is also r, because
Yes, sir.
this point lie on the periphery of the loop. So this
Yes,
the
sir.
point and this point are at a same distance from the wire. So here also the magnitude of the magnetic field will be same. So now here when we will find the direction of the magnetic field, we will apply the right hand rule, right hand thumb rule. So point your thumb in the direction of the current and curl 90 degree. Point your thumb in the direction of the current and point
Yes,
your
sir.
fingers along a point where you want to find the magnetic direction of the magnet and curl 90 degree. You will get
Yes,
the
sir.
direction of the magnetic field that will be
Outwards.
tangential,
Yes, sir.
inwards.
Inwards. Yes, sir.
You cannot say here inwards and outwards, because actually here what is the thing now? Here this loop is in YZ plane.
Yes,
Okay,
sir.
so but you should know means the direction will be tangential to the loop. Okay,
Okay.
now actually this loop now is in XZ plane, so no need of that now. What you will do, you will take the, you want to find this line integral of magnetic field. Okay, this is the line integral of magnetic field you want to find. V dot dl. Now take the small dl element on this loop. Okay, I am taking the small dl element. This is the dl, very small element of this loop dl, and the direction of this dl will be also along this. Okay,
Okay.
so I have told you that direction of the dl will be tangential. Okay, will be the direction of the current. Direction of dl will be the direction of the current, and direction of current is in this direction. So you will draw a tangent. You will get this dl, direction of dl. Now angle between the magnetic field and the dl will be 0 degree. Both are in same direction. Theta
Yes, sir.
is equal to 0 degree. Now we will open this. This will become v dl cos theta. This is the dot product of the magnetic field and this dl. So dot product of two vectors is given by a vector dot b vector is given by a into b, and cos theta is the angle between the two vectors. So you can compare this. So here magnetic field is constant throughout this loop. So I can take the magnetic field out of the integration.
Yes.
And here is, here this cos theta will be cos 0 and cos 0
Yes,
will
sir.
be 1.
Yes, sir.
Cos 0 degree is equal to 1. So here you will have dl now. This dl, integration of dl means you are just calculating small length of this loop throughout this loop, means you will get total length of the loop. So finally you will have v into total length of the loop, means the perimeter of the loop, that is 2 pi r. 2 pi r.
Yes.
Now we will apply the Ampere's law. Ampere's law says that the line integral of magnetic field is equal to mu 0 and the current enclosed by wire. So here na, the magnetic field at this point due to this long wire will be at a distance r will be mu 0 divided by 4 pi 2I by r, and this is multiplied by 2 pi r. This value, this V is the magnetic field due to this current carrying wire at this point. Okay, mu 0 divided
Okay,
by
sir.
4 pi 2I by r. So this is the formula you can see here. Infinitely mu 0 divided by 4 pi 2 pi divided by r. Magnetic field at a point A means at a point P which is at a distance A from the wire. So now this 2 pi and this we cancel out, this will become 2 and this 2 will be cancelled out with this, and this r will be cancelled out with r. So finally you will get mu 0 is equal into I. So this we have to prove that V dot dl is equal to mu 0 into I. So this is your LHS left hand side and this is your right hand side. So left hand side is equal to right hand side. Copy this.
Okay, sir. Done, sir. Done.
So you have to choose first the closed loop around the wire, and then
Okay.
you will calculate the line integral of magnetic field along that loop, and that line integral of magnetic field along that loop according to Ampere's circular law will be equal to mu 0 multiplied by the current enclosed by the loop.
Okay, sir.
Now see here. So there are some application of Ampere's circular law.
Sir, can you go
Application.
back? I didn't take the screenshots, the full screenshot.
Okay, no problem. Take it.
Yeah, can you scroll down, sir? Yes.
Done.
Yes, done, sir.
So now application of Ampere's law means we will apply the Ampere's circular law to calculate the magnetic field outside the cylindrical wire. So this is your wire. See the application of Ampere's circular law, magnetic field outside and inside of the current carrying cylindrical wire. Now first case I am taking, this is the cylindrical wire and of radius capital R. And in this wire along the cross section of the wire means through this cross section the current I is flowing. Okay. So
Okay, sir.
suppose this is the wire like this. This is also a cylindrical wire. So in this wire the current I is flowing in the upward direction, and I want a magnetic field at a point outside this wire. So what will I do? I will just imagine a Amperian loop, circular Amperian loop. I will imagine, and I will take this loop, this circular loop. See here, this is the circular loop you are taking.
Yes.
Okay, why you are taking this loop? Means the radius of this loop r, small r, which is greater than the capital R, because you want to calculate the magnetic field outside this wire. If you want to
Yes,
calculate the magnetic field inside, then you will take a smaller circular loop here.
yes, sir.
Okay, so same, all the things will remain same. This is the current carrying wire. Due to this current carrying wire, here is the magnetic field, and the direction of the magnetic field will be given by right hand rule, and that will be tangential. And this is your dl, a small length of this circular loop, and the direction of this loop will be also along this magnetic field, because the direction of the DL will be the direction of the current, and when you will draw the tangent you will get the direction of this DL also. This is the point P. And what is the angle between this magnetic field and the DL? 0 degree,
Yes, sir.
because both are in the same direction here. And this
Yes,
is
sir.
your amperian loop, circular amperian loop, because this is the cylindrical wire. And I have told you here, as if you have a cylindrical wire, see this point, for straight and the cylindrical wire, amperian loop is circular.
Yes, sir.
Okay. Now there are the few steps that you have to follow. First thing, you will consider a circular loop around the wire. Okay, so this is your step number first. Consider a circular amperian loop of radius r greater than a. Okay, so this is r, this is greater than small capital R. Here you get r greater than capital. Now you will calculate this v dot dl. Okay, you will calculate this v dot dl. You will calculate v dot dl along this loop. Yeah. Now open this v dot dl. This will become v into dl into cos theta. So finally you have v into dl cos 0. Cos 0 is 1, and you will take v out of the integration, and this is dl. So finally you will have line integral of magnetic field, that is equal to v into 2 pi r. This dl will be the length of this loop, that is 2 pi into small r. So this is your v dot dl. So this
Okay.
is your equation number 1. Now what you will do, you will uh, calculate current enclosed by this loop. What will the current enclosed by this loop? I is the current enclosed by the loop. So calculate I in. I in means current enclosed by loop. Ampere. I in is I, and now you will apply the Ampere's law. And what is Ampere's law? Ampere's law is this: mu v dot dl is equal to mu 0 into current enclosed by the loop. So v dot dl is this: v into 2 pi r. Simply we will put the value v into 2 pi into small r, mu 0 into what is the current enclosed? I is the current enclosed. So finally your answer will,
Yes.
you want to calculate the magnetic field at this point. So this is the
Yes.
magnetic field. V is equal to mu naught I divided by 2 pi r. And I in current inside the amperian loop, you can say, or I have already written, so we no need to write this. So this is the magnetic field outside the wire. Now suppose if I want to calculate the magnetic field inside the wire. So in that case, see here, inside the wire means somewhere here, like this. Here you can see. At this point, this is this point P lying inside the wire. And here you want to calculate the magnetic field at this point P. So here also you will consider the circular loop. But this time your circular loop will be smaller. The radius of your circular loop, small r, will be less than this capital R. Why? Because you want to find the magnetic field inside the circular wire, inside the cylindrical wire. This is the cylindrical wire. So this time your this small r will be less than the capital R. And again the magnetic field is B at this point P, and dl vector is this in this direction. Okay, so the direction of B and the dl vector will same, and so you can say the angle between both the vectors will be 0 degree. Now the main challenge is here to calculate the current passing through this cross section area. Okay, So first we will calculate this v dot dl here. V dot dl, you will open it, v into dl into cos theta. So finally you will get v into dl into cos 0, and cos 0 is 1, so you will have v into 2 pi into small r. This is your v dot dl. Magnetic field into 2 pi into small r. This is your equation number 1. Now what you will do, you will calculate the current enclosed by this area. Current
Yes.
enclosed by this area. So what is this area? This area is pi into small r square. So for this area, total area, the current will be I. Okay. For area, pi into capital R square, the current is I. Now, when you will calculate the current for this area, pi into small r square, so you will write this will be the current per unit area and multiplied by the area through which the current is passing. Means this is, you will do this, you will actually applying the unitary method here. Okay, I'm explaining it again. See, for pi r square area, the current is I. Okay, and you
Yes.
can say this for the unit area. When you will calculate the current for the unit area, you will get this amount of current passing through the unit area. Now, for pi r square area, the current will become I divided by pi r square multiplied by pi into small r square. You will multiply this pi r square with the current per unit area. Okay, this will be the current
Okay.
passing through the smaller area pi r square. So this
Okay.
pi and pi will be cancelled out. Your
Yes.
current will be I
I.
divided by r square divided by capital R square. So current enclosed or current n, you can write I divided by r square by r square. Now we will apply Ampere's law, that is v dot dl is equal to mu 0 into current
Yes.
enclosed by the loop. So v dot dl, we have v into 2 pi r. Mu 0, what is the current in I into r square by r square. R square by. Now magnetic field we can find. This r and r will be cancelled out. So your magnetic field will be mu naught r divided by 2 pi r square. So this is your magnetic field at a point which is at a distance of small r inside this wire. Okay, you can take the screenshots.
Okay.
Okay.
Done, sir.
Done, Ziyad?
Yes, sir.
So take this screenshot.
Done, sir.
Now this is the magnetic field calculation inside the wire.
Okay, sir.
This is a point here you are calculating the magnetic field. Scroll down.
Yes, sir. Oh, no, it's can you scroll up, sir? Sorry, sir.
Oh, no problem.
Okay, done, sir. Done, sir.
Now there is one graph
Done, sir.
also we will draw. We will check the variation of magnetic field with respect to the distance, okay, from the
Okay, sir.
axis of this wire. Okay, so means when you are going from this point to this point P, how the magnetic field is changing. So this graph is represented by this. When you are inside the wire, the magnetic field is directly proportional to R. You can see here this magnetic field is directly proportional to R. Okay, because this and this and this all are constant. And when you are outside the wire, the magnetic field will be inversely proportional to R. See here, outside the wire means this is the magnetic field outside. So this magnetic field is inversely proportional to this R. So this will be the straight line graph, and this graph will be the rectangular hyperbola. Okay. So just you can copy this graph. And this is the graph between the
Okay, sir.
magnetic field and R is the distance we know.
Yes.
So this is the. So here we have just applied the Ampere's law to calculate the magnetic field at some point. By using the Ampere's law, we have calculated the magnetic field outside the wire carrying the current I, and we have also calculated the magnetic field inside the wire carrying inside a point of the wire. Okay. Now here was a point I have written. See this point, magnetic field if the point lies on the conductor. So you can see this is the point lying on the conductor now. So with the help of Biot-Savart law, we cannot calculate when the point lies on the wire. Okay. So here I have written earlier cannot be
Okay, sir.
calculated by using Biot-Savart law, can be calculated using Ampere circuital law. So, so this was that point. Now next topic related to this is the solenoid. Solenoid we will have. Solenoid is nothing but a current carrying wire, and you have just folded that wire in the helical form. Solenoid is this. See, solenoid. This is solenoid. This is the wire, and this wire is folded like this in the helical form, and there is a current in this wire. I. So we know that a current carrying wire produces the magnetic field. So you can say this solenoid will behave as an electromagnet. Okay, solenoid, a type of electromagnet having number of turns of insulated copper wire carrying current. Okay, and L is the length of the solenoid I have considered. Capital R is the radius of the solenoid. Okay, this is the
Okay,
axis
sir.
of the solenoid.
Okay.
And small n is the number of turns per unit length of the solenoid. Means in a unit length there are small n number of turns, and I is the current for each turn. So this is the solenoid, and for the long solenoid means the length of the solenoid uh, very much greater than the radius of the solenoid. So this is the long solenoid. As this is the solenoid is behaves as an electromagnet, so we can say there will be some magnetic field. So the magnetic field due to the solenoid is given by this. See this figure. So this is the solenoid carrying the current, and this is the type of magnetic field line here we will have. So you can say in this region, in the central region, this is the central region. In the central region, the magnetic field lines are dense, means here the magnetic field is strong, and outside the solenoid the magnetic field will be less. Okay, so we
Okay.
can say that we can neglect this magnetic field outside the solenoid. Okay, and we can consider that here at the central region the magnetic field is constant. Okay, so
Okay.
there are some approximation for the long solenoid. You can say magnetic field outside the solenoid is negligible as compared to the inside. You can see by this figure also. Here the electric field lines are more dense, so you can say the
Yes, sir.
magnetic field is strong. Here is magnetic field is not that strong. Okay, here
Yes,
is
sir.
magnetic field as compared to here is negligible, and
Yes.
magnetic field in the central region is uniform. So here the magnetic field will be uniform.
Yes, sir.
Now we will see the cross sectional view of the solenoid for the calculation purpose. Okay. See, this is the bottle, and suppose I have cut this bottle from here. This is the bottle.
Yes.
I have cut this bottle from here like this, and the part you will see then will be a cross sectional view. So in the same way, we have cut the solenoid. Okay, we have cut this solenoid, and we will get this type of we will get this type of view. Okay,
Okay.
this type of view you will get
Okay.
when you will cut, and this cross represents the current going inside the solenoid, and this represents the current coming out of the solenoid. Okay,
Okay, sir.
from this figure you can imagine, suppose you are cutting this solenoid, so you will see here
Yes, sir.
at this point the current is looking like this, is going inside, and from
Okay.
here it will look like the current is coming out. So this is the figure.
Okay, sir.
Now this is the magnetic field. I have represented this magnetic field B, and this is the magnetic field B in the central region that we will calculate. So here we will use the Ampere's law, and now here I am taking the square loop. This time I am taking the square loop, and for
Yes, sir.
calculating the magnetic field. Now here why I am not taking the circular loop, because here when you will take the circular loop, the calculation of the line integral of magnetic field will be complex. So that is why I have chosen the square loop. Okay. So
Okay,
this
sir.
is the square Amperian loop. Square Amperian loop. ABCD. This is ABCD. So this is a square loop. So all sides of the square will be equal.
Yes.
So we have considered a square Amperian loop ABCD. Now first thing we will do, we will calculate the line integral of magnetic field along AB, BC, along this square you can say. So this is the line integral of magnetic field along the ABCD square. So this line integral of magnetic field, we have to do the line integral of magnetic field from to the whole square. Along the whole square we want to do. So what we will do, first we will do the line integral of magnetic field from A to B, then B to C, C to D, then D to A. So A to B, we will calculate the line integral of magnetic field, B to C, C to D, and D to A. Now this is A to B, A
Yes.
to B. Now this is the direction of the magnetic field. In this direction, the magnetic field is And direction of DL will also be along this direction,
Yes, sir.
because I have taken the direction of the loop in this direction.
Yes, sir.
This is the direction of the loop. So direction of DL and V here will be in the same direction. So you can say A to B. When you will open this dot product, this will be VDL cos theta, and this theta will be 0 degree. Okay, because the angle between B and DL here 0 degree. Now from B to C, this is from B to C. Now the direction of magnetic field is this, and the direction of DL is this. Okay, because you will take the direction of DL along the loop. So this DL and this magnetic field will be perpendicular, means theta here will be 90 degree. So you will use cos 90 here. V into DL. Now I am opening this V into DL cos 90. Now from C to D, you are going from C to D, and this point lies outside the solenoid. So C to D, there will be no magnetic field. See here, magnetic field in the central region is uniform. That is this magnetic field, but the magnetic field outside the solenoid is negligible as compared to the inside. So here the magnetic field will be negligible, means 0. Okay. So here from C to D, the magnetic field will be 0. The whole term will become 0. From D to A, see from D to A, this is D, this is A. So the magnetic field direction is along the x direction, and DL direction will be along the negative y. So the angle between the magnetic field and the DL, see here, this will be the DL here. And the direction of the DL will be in this direction, and the magnetic field is in this direction. The angle between the DL and the magnetic field will be 90 degree. So here you can write B into DL cos 90 degree. And you should know cos 90 degree is equal to 0. Okay. So from A to B, this will become only B into DL, and cos 90, this whole term will become 0. This is also 0, and this whole term will become 0. So we have only this B dot DL. And this magnetic field B in the central region is constant, so we can take this magnetic field outside. Now it will become B into, this is DL from A to B. This is DL from A to B. So DL from A to B will become AB, length AB. And I am just supposing the side of this square as A. Square amperian loop of side A, small a. So this AB will be A because this is a square. All sides are equal. B into A. So line integral of magnetic field, you will have this term, you will have here, you can write. So line integral of magnetic field along the square ABCD is equal to VA. This is your equation number 1. Now what we will do, we will just calculate the current enclosed by this loop, and for that N, capital N, I am assuming the number of turns, total number of turns, I am supposing capital N,
Okay, sir.
total number of turns. And small n is the number of turns per unit length. Number
Okay,
of
sir.
turns per unit length. Okay. Now we want to calculate the current enclosed by this loop. Okay. So current enclosed by this loop will be the I into capital N. See, just a minute. There are total number of turns n.
Yes.
Okay. See, just a minute. We want to calculate the current enclosed by this loop.
Yes.
So we will take the help of this small n. Small n is the current per unit length. So small n is equal to, not the current per unit length. Small n is the number of turns per unit length. Okay, so n is the number of turns per unit length. Okay, of the solenoid. So when you will calculate current enclosed by the loop, current enclosed by the loop, so this will become small n into, just a minute, into I. I'm removing this. Now, see, small n is the number of turns per unit length. So suppose I am supposing the square loop. Okay, I have supposed. So n will be the n, suppose the number of turns per unit length of the square. So total number of turns turns for the square will be NA, and each turn carrying the current I. Each turn carrying the current I. So NA turn will carrying the current INA. Okay. So total current enclosed by square is equal to current enclosed by one turn divided by total number of turns. N is the total number of turns for the square loop.
Yes, sir.
So this is your total current. I have
Okay.
taken the help of this small n. So this is the total current enclosed by the loop. That is, this is I in. Now we will apply the Ampere's law, Ampere's circuital law. That is, line integral of magnetic field V dot dl is equal to mu 0 into current enclosed by the loop. So
Yes.
V dot dl, we have this. V dot dl is this. V into A. V dot dl is VA. So write here V into A, and mu 0, what is current enclosed? I into small n into A. So this is I into small n into A, and this A and A will be cancelled out. So the magnetic field you will have mu 0 into small n into the current I. This is the magnetic field we given by this formula. So this is the magnetic field along the axis of the Means you can say along the central region of the solenoid. Okay, so this is the formula you will get finally. So what we have done, this is the cross section view. We have just choose a square loop, and we have done the line integral of magnetic field along this square loop. So we will get this. Okay. Now we will calculate. After that, we will calculate the current enclosed by this loop, and for that we need this small n. Small n is the number of uh, turns per unit length. So this
Yes,
square
sir.
have the length a. This square have the length a, means all side of the square is a. Okay.
Yes, sir.
So you will calculate n by a. Okay, this is
Okay, sir.
small n, and here from here you can calculate the number of turns for the square loop is na, and current enclosed by each turn is I. So current enclosed by NA turn will be INA. So then you will apply the Ampere's law and you will get this formula. Okay, when you will do the practice this derivation one or two times, then you will get all the things clearly. Okay,
Okay, sir.
now you can take the screenshot.
Okay, sir. Done, sir.
Okay.
Yes, sir.
So remember, this is the solenoid, this type, and this represents the just magnetic field distribution. Taken.
Yes, sir.
This cross sectional view, you should know, this is the cross sectional view of the solenoid.
Okay, sir. Done, sir.
And after that, you will choose a square loop and you will do the line integral along that square loop. Some mathematics is involved here.
Yes, sir. Done, sir.
Sorry.
Done, sir. Yes.
And this formula you should remember.
Okay, sir. Yeah, done, sir.
So there are node points. Suppose in this solenoid, I have placed the some material, means a core of some material I have placed. So in that case, what will be the magnetic field? So if core of solenoid, core of solenoid if a core of material having permeability mu r is inserted, then the magnetic field will become mu r mu 0 and into r. You will simply multiply this total magnetic field with this mu r, means the relative permeability of that material.
Okay, sir.
and this is the magnetic field. This is the magnetic field B in the central region. If you want to find the magnetic field at the ends of the solenoid,
Yes.
so there is only formula. Magnetic field at the ends of the solenoid will be half of the magnetic field you have calculated for the central region. Mu naught, mu 0 and I. This will be mu 0 small n into I. So for this formula, no derivation is your, means the derivation part is not in your syllabus. So this formula you can remember if someone is asking the magnetic field at the end point. Take the screenshot of this part also.
Then
So this question is based on the solenoid topic. So here they are saying a 90-meter long solenoid has 6 layers of windings. 90-meter long solenoid have 6 layers of windings of 450 turns each. Means in a solenoid there are 6 layers, and for
yes,
each
sir.
layer there are 450 turns.
Yes, sir.
So total number of turns, what will be the total number of turns?
450 into 6, right?
Very good. Total number of turns represented by capital N,
Yes, sir.
that will be 450 into
6.
6.
Yes, sir.
Now they are saying if the diameter of the solenoid is this and the current is 6 ampere. So current in the solenoid is 6 ampere. Then find the magnitude of magnetic field near its center. So magnetic field
Yes,
at the
sir.
center is given by this formula mu 0 small n into I.
Yes, sir.
So mu 0 is given by 4 pi into 10 to the power minus 7, and small n is capital N divided by length of the
Yes,
solenoid.
sir.
Small n is the number of turns of the solenoid divided by the length of the solenoid. Number of
Yes.
turns per unit length. And current is 6 ampere.
Yes,
So
sir.
from here we can calculate this 4 pi into 10 to the power minus 7. This capital N is 450 into 6 divided by the length. Length, where is length? Length is
90 meter, right?
90 meter. 90 meter.
Yes, sir.
90 meter is very, very long. So you can write
Yes,
here
sir.
90. Actually,
So
this will be
90
90
centimeters.
centimeter.
Yes, sir.
90 centimeters. So you will convert this 90 into meter. So
Yes, sir.
90 into 10 to the power minus 2. And finally, you will multiply this with the 6.
Okay, sir.
When you will calculate, you will get the answer 72 into 10 to the power minus 4 Tesla. You can calculate this by yourself also.
Okay, sir.
Note it down.
Okay.
So this type of question you will get. But you should know this formula. What
Okay,
is
sir.
the magnetic field near the center? In the central region, the magnetic field is given by mu 0 small n into I. Small n is capital N divided by N.
Okay, sir.
So toroid, we will not drive the magnetic field for toroid, and we will
Yes.
just know what is toroid. And So toroid is, suppose you have a solenoid, you have this solenoid, suppose the earlier solenoid we have used. This solenoid we have, and I have just bent this solenoid in the circular form. So this will become
Yes,
a
sir.
toroid. This will become
Okay,
a
sir.
toroid. So this is the toroid, and this toroid is a circular solenoid, you can say, and this consists of a number of turns of insulated wire on a circular core. You have taken a circular core and you have just bind that core with some wire. Okay,
Okay, sir.
so just note this down, only these 2 points.
Only the 2 points, sir.
Yeah.
Okay, sir. Done, sir.
Just when your exam will be conducted?
Physics, right, sir?
Yeah, physics.
So physics exam is on 5th, sir. Yes.
This means day after tomorrow.
Yes, sir.
Tomorrow and day after tomorrow. Okay. So which chapters are coming?
So magnetism, sir.
Magnetism. So do you have any doubt in the magnetism? You can ask me.
So magnetic effects and alternating currents.
Acha, magnetism.
Yeah. Magnetic effects, only the numericals are coming, sir.
Only the
For ma-
numericals are coming. So for the
Yes, sir.
numerical, na, so what you should do na here? From here I have started. So for the numerical point of view, you should know all the basic formulas like this Biot-Savart law. Okay.
Okay, sir.
I
Okay,
have
sir.
made the star also which formula you have to learn. Like here from the question you can understand. Means this
Yes, sir.
formula you should know. Okay. The formula
Okay,
of the
sir.
magnetic field. And now here are some important formulas. Like what is the formula when the current is flowing in the wire?
Yes,
Okay.
sir.
So this is the magnetic field.
Okay, sir.
And what is the formula due to an infinitely long wire? This is the formula. So mu 0 divided by 4 by 2 I by a, and this is another formula for the semi-infinite conductor. This formula, and due to a point lies along the length, the magnetic field will be 0. So these points you should know for the numericals. And here we have done yesterday this circular arc, semicircular
Yes,
wire.
sir. Yes,
So
sir.
and we have done the questions also. These questions. And then Ampere's law. You should know this Ampere's law and how to apply the Ampere's law. How to choose the Amperian loop. Okay.
Okay, sir.
So till now we have discussed the magnetic field due to the straight wire, and that straight wire can be infinitely long, can be semi-infinite wire. And after that we have discussed the magnetic field due to the circular arc. Okay. And semicircular wire and the circular wire. And then we have discussed the magnetic field at the axis of the circular coil. And after that, I have discussed what is the Ampere's law and the application of the Ampere's law.
Yes, sir.
And after that, we have discussed the solenoid.
Yes, sir.
So one more topic I am discussing, and it will take at hardly 5 minutes. So Lorentz force. Now we have seen that whenever electric charge is in electric field, it will experience an electric force that is given by charge into electric field. Now, if that charge particle, suppose, is in motion in the magnetic field, then that charge particle will experience the magnetic force. Earlier, the charge particle was in the electric field, was experiencing the electric force, and now the charge particle will experience the magnetic force when the charged particle will be in the magnetic field.
Yes.
So see now, this is your now this topic is the Lorentz force, and this is also known as magnetic Lorentz force. And
Yes.
here is the magnetic field. This is your magnetic field, and this is your charge particle. And this charge particle is moving in the magnetic field along this direction. And this charge particle having the velocity vector v vector, the velocity
Yes.
v. And this magnetic field in which the charge particle moving is uniform. So the force, there will be force on the charge particle, like the electric force.
Yes, sir.
If this charge particle will be in the electric field, then this charge particle will have the electric force. Now this
Yes.
charge particle is in the magnetic field. There will be the magnetic force on this charge particle, and this magnetic force is given by this formula. Magnetic force is equal to Q into velocity of the charge particle V cross B. And this is also given by QVV sine theta. And what is theta? Theta is the angle between this magnetic field and the velocity.
Yes.
Angle between magnetic field and velocity.
Yes.
So this will be the magnetic force on the charge particle. Like the electric force on the charge particle will be given by Q into electric field. Here the magnetic force is given by QVV sine theta. Now, what will be the direction of this force? For the direction of this force, we will again apply the right hand rule. Right hand rule here says that point your fingers along the direction of the velocity and curl it towards the magnetic field. Point your fingers towards the direction of the velocity and curl towards the magnetic field.
Okay.
So when you will do that, you will get the direction inwards. So this
Yes, sir.
direction of this force will be inwards. You will get inwards means this cross. Okay. And
Okay.
this magnetic force is a cross product of velocity vector and the magnetic field vector. Okay, so you can say this magnetic force will be perpendicular to the velocity and will be perpendicular to the magnetic field. Okay, so this is
Okay.
also given by the right hand rule. Place your finger along the velocity and curl it towards the magnetic field. Thumb will give you the direction of the force. Okay? And here is your positive charge. Okay, then and now suppose there is negative charge. So for the negative charge, what you will do, the direction of the force will be opposite to the one obtained by the right hand rule. So suppose the negative charge is moving in this direction. So what you will do, you will consider that charge as a positive charge, and that charge is moving like this, and you will find the force. And suppose if you are getting the magnetic force inwards by the right hand rule, then you will consider the direction of the magnetic force outward in that case, if your charge will be negative. Okay, just note it down.
Okay, sir.
So electric force is QE and magnetic force is QVV sine theta.
Okay, sir.
Yeah, okay, yeah. Just take the screenshot of this.
Done, sir.
So right hand rule says that point your fingers along the direction of the velocity and curl your finger along magnetic field towards magnetic field.
Yeah. So
Point
yes,
your
inwards, sir.
finger, yeah, inwards. Suppose
Yes,
the
sir.
velocity, this charge is going in this direction. So what you will do? Point
Downwards,
your
sir.
finger in this direction
Yeah,
and
downwards.
curl toward the magnetic field. So the magnetic
Towards
force
me.
will
Yeah.
be towards you. And
Yes, sir.
this both the formula you should know.
Okay, sir.
I'm highlighting it. This formula is important. Taken the screenshot?
No, sir. Just a second.
Okay. And this FB will be the magnetic force. This charge in the magnetic field is in the magnetic field. So this force will be the magnetic